The situation involving ungrounded light poles presents a significant safety hazard that demands urgent and thorough remediation. Utility companies, while frequently exempt from local inspections, bear a critical responsibility for guaranteeing the safety and reliability of their electrical installations. This discussion addresses the dangers associated with relying solely on ground rods for fault current return paths, particularly in the absence of equipment grounding conductors, and explores viable solutions for enhancing electrical safety. The absence of an equipment grounding conductor, or EG, in the described scenario raises serious concerns regarding fault current pathways. In a properly grounded system, the equipment grounding conductor provides a low impedance path for fault current to return to the source, which is typically the transformer. This low impedance path facilitates the rapid clearing of overcurrent protection devices, such as circuit breakers or fuses, thereby minimizing the duration of a fault and reducing the risk of electrical shock or fire. When relying solely on a ground rod for fault current return, the impedance of the grounding path can be significantly higher due to the resistance of the soil. This elevated impedance can impede the flow of fault current, potentially preventing overcurrent protection devices from operating promptly. Consequently, exposed conductive parts of electrical equipment, such as light pole housings, may become energized during a ground fault, posing a substantial shock hazard to individuals who come into contact with them. Furthermore, inadequate grounding can contribute to voltage rise on grounded metal parts, increasing the risk of electrical shock. The interpretation of Massachusetts General Law, or MGL 166.32, asserting jurisdiction over electrical installations within a city or town, including those supplied from buildings and structures, is a crucial point. Pursuing a ruling from the town council to solidify this interpretation is a prudent course of action. It is essential to meticulously document the dangerous conditions observed, gathering evidence to support the claim of non-compliant installations. This documentation may include photographs, measurements of grounding impedance, and detailed descriptions of the wiring methods employed. Engaging with local state representatives or senators can provide valuable assistance in influencing the utility company to address the safety concerns. Legislators can exert pressure on the utility to prioritize safety and adhere to relevant electrical codes and standards. Filing a formal complaint with the state's Public Utilities Commission is another avenue to explore. The Public Utilities Commission is responsible for regulating utility companies and ensuring that they operate in a safe and reliable manner. A formal complaint can trigger an investigation and potentially lead to corrective actions. Seeking technical support from a local electrical contractor or engineer can be invaluable in assessing the extent of the problem and developing effective solutions. These professionals can provide expert advice on grounding techniques, overcurrent protection, and compliance with electrical codes. They can also assist in drafting a formal complaint or request for inspection, presenting a strong case for corrective action. Educating homeowners and residents about the risks associated with ungrounded light poles is an essential step in raising awareness and promoting safety. Informing them about the potential shock hazards and encouraging them to contact the utility company to express their concerns can amplify the pressure on the utility to address the issue. Addressing this specific question regarding the equipment grounding conductor, running the equipment grounding conductor all the way back to the transformer's X0 connection is the most comprehensive and reliable approach to grounding. This method ensures a low impedance fault current path directly back to the source, facilitating the prompt operation of overcurrent protection devices. If it is not feasible to run the equipment grounding conductor all the way back to the transformer, ensuring that the equipment grounding conductor is appropriately sized for the circuit and provides a low impedance fault return path is crucial. The size of the equipment grounding conductor should be determined in accordance with the National Electrical Code, or NEC, Table 250.122, based on the size of the overcurrent protection device protecting the circuit. In addition, it is important to verify that the connections of the equipment grounding conductor are secure and corrosion resistant. While using a ground rod at the pole base can provide supplementary grounding protection, it should not be relied upon as the sole means of grounding. Ground rods may not provide a consistently reliable ground in all soil conditions, particularly in areas with dry or rocky soil. The effectiveness of a ground rod depends on its contact with the earth and the soil's ability to conduct electricity. Therefore, it is essential to supplement ground rods with an equipment grounding conductor that provides a direct, low-impedance path back to the source. It is important to emphasize that the neutral conductor should always be insulated at the pole connection. Failure to insulate the neutral conductor can create a potential shock hazard and compromise the integrity of the grounding system. The neutral conductor should be insulated to prevent it from coming into contact with grounded metal parts, such as the pole housing. The NEC mandates that electrical equipment be installed in a neat and workmanlike manner. This requirement extends to the installation of grounding conductors and connections. Grounding conductors should be properly supported and secured to prevent them from becoming damaged or disconnected. Connections should be made using approved connectors and methods to ensure a reliable electrical connection. In addition to the NEC, other relevant standards and guidelines can provide valuable information on grounding and electrical safety. National Fire Protection Association, or NFPA, 70E Electrical Safety in the Workplace offers guidance on safe work practices for electrical workers. Institute of Electrical and Electronics Engineers, or IEE, Standard 142, Recommended Practice for Grounding of Industrial and Commercial Power Systems, provides detailed information on grounding system design and installation. Furthermore, it is imperative to ensure that all electrical work is performed by qualified and licensed electricians who are knowledgeable about electrical codes and safety practices. Unqualified individuals should never attempt to perform electrical work, as this can create a serious safety hazard. Regular inspections and maintenance of electrical systems are essential for identifying and addressing potential problems before they lead to accidents or injuries. Electrical systems should be inspected periodically by qualified electricians to ensure that they are in good working condition and comply with applicable codes and standards. Maintenance should include checking grounding connections, testing overcurrent protection devices, and inspecting wiring for damage or deterioration. In conclusion, the situation described involving ungrounded light poles poses a significant safety hazard that requires immediate and comprehensive action. By pursuing a legal interpretation of MGL 166.32, documenting the dangerous conditions, engaging with legislators and regulatory agencies, seeking technical support, educating the public, and implementing proper grounding techniques, the risk of electrical shock and fire can be substantially reduced. Remember that electrical safety is paramount, and all electrical work should be performed by qualified professionals in accordance with applicable codes and standards. The presence of overload and short-circuit protection is paramount for the safety of any electrical circuit. Circuits directly tied to the secondary of transformers without such protection pose a significant risk of overheating, fire, and equipment damage in the event of a fault. Overload protection devices, such as circuit breakers or fuses, are designed to interrupt the flow of current when it exceeds the safe capacity of the circuit conductors. Short-circuit protection devices are designed to rapidly interrupt the flow of current in the event of a short circuit, which is an unintended connection between two conductors. The absence of these protection devices can allow excessive current to flow through the circuit conductors, causing them to overheat and potentially ignite nearby combustible materials. This is a serious safety hazard that must be addressed immediately. Moreover, the absence of overload in short-circuit protection can damage or destroy electrical equipment connected to the circuit. Excessive current can cause equipment to overheat, melt, or explode, resulting in costly repairs or replacements. Therefore, it is essential to install appropriate overcurrent protection devices to protect both the circuit conductors and the equipment connected to the circuit. The National Electrical Code, or NEC, provides detailed requirements for overcurrent protection. Section 240.4 of the NEC specifies the requirements for protecting conductors against overcurrent. This section requires that conductors be protected at their ampacity, which is the maximum current that a conductor can carry safely without overheating. The ampacity of a conductor is determined by its size, insulation type, and installation conditions. Section 240.21 of the NEC specifies the requirements for overcurrent protection of transformer secondary conductors. This section allows for certain exceptions to the general rule that conductors must be protected at their opacity. However, these exceptions are subject to specific conditions and limitations. In general, the overcurrent protection device on the secondary side of a transformer must be sized to protect the transformer and the secondary conductors. It is crucial to carefully review and comply with the requirements of the NEC to ensure that electrical circuits are properly protected against overcurrent. In addition to the NEC, other relevant standards and guidelines may provide further information on overcurrent protection. These standards may include those published by the Institute of Electrical and Electronics Engineers, or IEE, and the National Fire Protection Association, or NFPA. It is also important to consult with qualified electrical engineers or contractors to ensure that overcurrent protection systems are properly designed and installed. Regular inspections and maintenance of overcurrent protection devices are essential for ensuring their continued reliability. Circuit breakers and fuses should be periodically tested to verify that they are functioning properly. Connections should be checked for tightness and corrosion. Any damaged or defective devices should be replaced immediately. Furthermore, it is important to train personnel on the proper operation and maintenance of overcurrent protection systems. Personnel should be familiar with the location of overcurrent protection devices, their operating characteristics, and the procedures for resetting or replacing them. Proper training can help to prevent accidents and ensure the safety of electrical systems. In conclusion, the absence of overload and short-circuit protection on circuits directly tied to the secondary of transformers is a serious safety hazard that must be addressed immediately. Appropriate overcurrent protection devices should be installed to protect both the circuit conductors and the equipment connected to the circuit. The National Electrical Code, or NEC, provides detailed requirements for overcurrent protection, and these requirements should be carefully reviewed and complied with. Regular inspections and maintenance of overcurrent protection devices are essential for ensuring their continued reliability.